All right, welcome everyone. This is the IEEE exam review, exam 1 review for EECE 2310 with Professors Kogan and Ahmed. So there's a lot that we should get through, and there's a lot of things that we could spend a lot of time doing examples on. So I have a list of some things that I've prepared. Please, at any point, let me know if there's something that you talked about in class that I haven't talked about on here, because sometimes the course changes throughout the years. And then also let me know if there's anything that's too easy or too hard, if you want to spend more time on something, because we can really tailor this the way we have. But I do have a set of material prepared. So 2310, starting off, I figured we could talk about the logic gates. So as I understand it, you need to understand the difference between NMOS and PMOS. I don't think that you're going to be required to draw out like an AND gate using NMOS and PMOS, but I think you need to understand when they turn on, when they turn off. So let's go over that quick. So NMOS looks like this without the inversion bubble. And for this one, I always try to remember it as like normal, like the N stands for normal. Whereas PMOS, of course, has the inversion bubble. And I like to think of that as like opposite. But as long as you can remember that the N is normal and then the P is the other one, it's the other way, then that works. Okay? So, yeah, peculiar, I like that. Peculiar. So, NMOS, PMOS. So if your input, which is like this input here, if your input is a 0, then an NMOS will be off, right? And that's kind of normal. That's kind of what you would expect. If the input is 0, it's off. If it's 1, then it's on. And remember, when it's off, that means it's no conducting. And when it's on, yes, conducting. And everything is opposite for the PMOS. So in a PMOS, if your input is 0, then it is on. Or, yeah, it's on. And that means it's conducting. Whereas if your PMOS has an input of a 1, that's off, which means that it is not conducting. So what you might be asked to do on an exam is they'll give you a schematic of an AND or an OR something even more complicated, and they'll say for this input, which CMOS transistor is on, which is off, and what's conducting. So be prepared for that. I think you don't need to remember how to draw these things from memory, but if you remember this much, and so for example, the easiest gate to make, right, is an NAND and NOR and an inverter. So real quick, let's just go through like a NAND. So that starts out, you've got your VCC, and this you have the two, we'll call this NAND is A NAND B equals C, right? So this one can be A, and then this next one is B. Notice these are both PMOSs on the top. And I don't think you're going to be asked to draw these things from memory, but this is just as an exercise so we can look at when they're on and when they're off. So then we're going to have our NMOSs, our normal ones down here. One of them is going to be A, one of them is going to be B, and then this is your ground. Okay, and then this is your output C. So try and leave that on the screen as much as I can. So for our NAND gate, remember, let's draw a little truth table. 0, 0, 0, 1, 1, 0, 1, 1. So NAND, it's the opposite of AND. So for AND, you have a 1 here and 0s everywhere else. NAND is opposite. So you have 1s here and 0 when they're both high. is B is not connected to C. C is just this entire node here. Or yeah, like this is connected here, this is connected here. This entire node is your output C. So let's do an example. Okay, so let's get a different color here. And let's say we're looking at this case where A is 0 and B is 1. So we can say A is 0, B is 1, A is 0, B is 1. So we'll look at each of these transistors and say whether they're on or off. So I'll get a highlighter out here, and I'll highlight it green if it's on and conducting, and red if it's off and not conducting. So if A is a PMOS transistor and it has an input of 0, then that means that it is conducting. So this one would be on, right? And that's from up here. If the input is 0 and it's PMOS, then it's on, it's conducting. The other A transistor also has an input of 1, but that's NMOS, that's normal. So this one's going to be off. Okay, so we can highlight this one red, meaning it's off. Well, that doesn't work very well. This one is off. Okay, just try and remember that. Likewise, this top B one has a 1 and it's PMOS, so that means it's off, it's not conducting. Okay, so this one is also not conducting. Whereas this bottom B, this one is an NMOS and it has a 1, so that means it is conducting. So if you want to know what the output of this circuit will be, you can look. Once you've figured out which the transistors are conducting or not, we see that this is essentially a break in the circuit. This transistor is not conducting. There's a break here, so this ground cannot access the output C. But where we don't have a break is VCC here has a conduction path all the way to the output. So our VCC is like a logic 1. That means our output is directly connected to VCC, and that's why our output is a 1. So in this case, our output is 1. So does this make sense? We're looking at each of the transistors, looking at their inputs, and figuring whether they're conducting or not conducting. You might have a question like this on your exam. I know when I took this class, I had a question like this on my exam. So be prepared to do that. But it doesn't get a lot more complicated than that, right? The B truth table? But yeah, so yeah, A and B are the inputs, so they can be whatever. If maybe, so this is a NAND gate, right? If they gave you an AND gate, remember the NAND gate, or the AND is just the NAND connected to a NOT. Okay, so that's like what an AND gate is. So you could imagine that they would have more transistors here for the NOT gate if you were given the AND gate on the circuit. And then you just do the same thing. You'd have 2 more transistors to look at. And they might say, like, they might have this one highlighted and be like, is this transistor on for this case? So you'll just go through those steps and just remember this kind of table, this table. Okay. Yeah, this is the same as C. Yeah, that's the same as C. Okay, and you can just like think about like the truth table for NAND. So we can go through just as a review the truth tables for all the different gates. I think that'll be useful. So any more questions about this type of thing? Okay, we'll move on real quick. So next we'll just look at kind of all the gates that you need. So say our inputs are A, B. These are inputs, right? Maybe I should give myself a little more room. So A, B, this is going to go 0, 0, 0, 1, 1, 0, 1, 1. Okay, and is easy. And remember, the gate looks like this. So this is going to be 0, 0, 0, 1. NAND, right, is the opposite. And the symbol looks like an AND gate with an inversion bubble on it, and it's going to be the opposite of that one, 1, 1, 1, 0. Okay, we can do OR as well. OR looks like the pointy one. Remember, that one's always hard to draw. I was never good at that. I am using a tablet, but because it doesn't look good, I'm going to pretend like I'm using a mouse, and then it just looks so good for using a mouse. So OR, remember, is 0 when both the inputs are 0. Otherwise, it's 1. If either A or B or both are high, NOR is OR gate with an inversion bubble. That's going to be the opposite of OR, so 1, 0, 0, 0. And then kind of the ones that I think are a little trickier is the XOR. Okay, well, we'll talk about XOR. XOR is exclusive OR. So sometimes like, yeah, either but not both. Okay, so when it's 0, 0, neither of them are true. So that's the output is 0. If exactly one of them is high, then the output is high. But then if both of them, then it's 0 again. So it's exclusive OR. It means one or the other, but not both. And then XNOR is very similar. Okay. It looks like an XOR with an inversion bubble. And it is, you guessed it, the exact opposite. It's either neither or both. Okay. So it gets a little weirder when you have more than 2 inputs. It's pretty easy to wrap your head around like this, but when you have multiple inputs like 3, 4, 5, you can use these to kind of check for parity or if there's an odd number of inputs. So, for example, the XOR, right, when there's an odd number of inputs, the output will be high. So I don't know if you'll need that for this class, but that's just a little fun fact. But these are probably all the gates that you'll need to talk about, other than like not, right? But not as easy as just the opposite of the input. So in this case, A naught, B naught would be 1, 1, right? For this first case. Okay, and then that looks like that is a NOT gate or an inversion. Okay, let's move on because we have a lot to get through. So next, Boolean algebra theorems. So you're probably going to be asked, you're going to be given an equation and say, simplify this down to SOP or POS in the simplest form. So some of the most important principles, identity, right? What that is, there's kind of an AND version and an OR version for all of these. So for AND, identity means like 1 and A equals A. And for OR, it means 0 or A equals A. Okay, that one is pretty intuitive, I think. One that's really useful is distributive. So the distributive property for AND is it looks like if you have if you're distributing over AND, A or BC is the same as A or B, A or C. Okay. So distributed works kind of both ways. For the other case, it would be A and B or C. This one is kind of like normal algebra. A and B or A and C. Okay. And I would say that this one, because it's a little unintuitive that you can distribute this OR over AND, this one is one where you might not, you might get stuck at this step in your simplification. So don't forget that the distributive property works equally well for both AND and OR. Okay. You can think of like you're distributing this this A OR to this one and to that one. Okay. Some of the other important properties, De Morgan's law. right? So for and, if we're De Morgansing and, A B naught equals A naught or B naught. A or B, all knotted, is A naught, B naught. So remember, when you're taking this inversion to the inside, you have to invert all of the terms and change the symbol between them. That's all happens in one step. You invert the terms and you change the symbol between them. So that's De Morgan's law. There's another one that you might not have talked about in class, because you can derive it pretty easily from the other ones. But this one is also pretty useful for simplifications if you use it correctly. So what this one says is A and A plus B is just A. And in the other case, it works the same way, where A or AB is just A. We can do a little bit of a proof for this one because it doesn't look it looks too good to be true, right? You might think, how can we get there to there? So let's prove this or one first. We can kind of factor out an A, so we can get A and 1 or B, right? So this we're factoring out an A, so then the left-hand A becomes a 1. We get rid of the A here, and we're just left with a B. The 1 or B is always going to be 1. And that's by the, what is that, the identity with or not the identity, yeah, no, yeah, that's the thing is, for this exam, I don't think you need to know the names of the properties, but just know how to use them. Yeah, it's something like there's different names for it in different books. So then this becomes just A, because A and 1 is A. And we kind of use this for the next step. So if we were to distribute out this A on this side, so we get A and A, or A and B. A and A is just A, right? And that's the idempotent property. So this is just A. And here we have exactly what we started with over here. So then this will also simplify down to just A. So these ones, if you can notice, if you can recognize this in your problems, this will save you a couple of steps, but you can clearly get from one to the final one. And I don't remember going over this one in class, so just in case this helps, I hope that it does. But otherwise, we can do an example using these properties, maybe. Time is going much more quickly than I expected. So minimize in SOP. So SOP, this is sum of products, right? So if we want to minimize this, we can kind of pair up some terms and look to see what we have in common. So if you look at these two terms, both of them have an A naught B. So we can factor out the A naught B and then say C or C naught. That's what's left. Okay, and let's just focus on this term. C or C naught is going to be 1. Because one of these is going to be 1 and the other one's going to be 0. You're ORing them together, so that's going to be 1. So then this just becomes A naught B and 1. So just A naught B. Okay, so I get to write that in 2 steps. A naught B and 1 becomes A naught B. The next one, these two terms, they both have an A B naught in common. So we could say A B naught, C naught, or C. In the same way, C naught or C becomes 1. So this becomes A B naught and 1, which is just A B naught. We can OR these together, and there's no further simplifications that we can do on this. So this would be our most simplest SOP form. Do you guys feel pretty good about applying these rules, these properties? There's probably going to be like one question about those. The rest of the simplifications you'll be doing with K-maps probably. That's probably the big topic of this one is K-maps and working with these big equations. So you'll need to know this stuff, but if you're ever in the future, yeah. Okay, so yeah, sorry, I noticed these two both have A B naught. The only difference is C naught and C. So I factored out the A B naught from both of them, and I was left with C naught or C. Okay. Yeah.
I was actually say, not really per se asking this, but is there any way that we can go over two sometime?
Yeah. So 2's complement is. So you guys feel pretty good because there's the numbers and the base conversions and the K-maps. There's a lot to get through. So if you guys feel pretty good about this, we can probably skip some of these like SOP to POS things and come back to them if we have time. But 2's complement?
Yeah.
Okay. How about let's do that right now. Let's start with the binary base conversion, stuff like that, and then that'll lead into 2's complement. So base conversion, binary arithmetic. So binary works, right? You have all your digits, and each one represents a different thing. This is the 2 to the 0. This second digit represents 2 to the 1, 2 to the 2, and you'll either have 1 copy of 2 to the 0 or 0 copies of 2 to the 0, right? So every binary number can be written like this, and every number can be written in binary. So for example, if we had the number 67, we could write this as, so this is like 64 plus 2 plus 1. And I know that your professor probably showed you 2 ways of getting from decimal to binary. One of them is through division, and one of them is through addition. I learned it this way, but we can go over both ways in a sec. But so right, 67 is 64 plus 2 plus 1. 64 is, if you need to draw out a table, you can. That's 2 to the 6 plus 2 to the 1 plus 2 to the 0. So 67 has 1 copy of 2 to the 0. That's our first one. 1 copy of 2 to the 1. 0 copies of 2 to the 2. And then 2 to the 3, 2 to the 4, 2 to the 5, and then 1 copy of 2 to the 6. So this would be 67 in base 10 equals this in base 2 in binary.
It's to write, right? We wouldn't go 8 bits into like that.
Unless you were specifically asked, like, write this in 8-bit binary, you probably don't. You can probably leave off these trailing zeros, these leading zeros. Now, when we get to 2's complement, the answer might be a little bit different, but not too different. So, how do you guys feel about converting between decimal and binary? So to go the other way, right, we would notice that this is 1 times 2 to the 0. This is 1 times 2 to the 1. And this is 1 times 2 to the 6. And we just add those all up. We can do more examples, but I think 2's complement is 2's complement and K-maps are like the big beast of this exam. Okay, so let's talk about 2's complement. So 2's complement, in binary, you were just talking about this. So what is this number in decimal? This is 5, yeah. 5 in base 10 is this in base 2. If we write 0, 1, 0, 1, that's also 5. So we can add, if it's a positive number, we can add as many leading zeros as we want. When we're working with 2's complement, our number system changes a little bit. This is still 5, but we need an extra bit. We need an extra bit to represent the same range of numbers. So, for example, say the numbers that we're working with are between 0 and 8. The biggest number we want to represent is 8 or 7. We're working between -8 to +7. You might think that 7 only requires 3 bits to write. That's 1, 1, 1. But because we're working with 2's complement, we need an extra bit. So step 1 for 2's complement is what I would recommend, so you don't get messed up with any like 1s or 0s in front, is figure out what's the world that you're working with. How many bits do you need? What's the biggest number that it might represent? And they might tell you that. They might say 4-bit 2's complement or something, or they might give you a range of numbers or something like that. Yep. It might, or it might just say subtract these 2 binary numbers. But anytime you have to make a negative binary number, you'll use 2's complement. So it might not say do 2's complement specifically, but you might have to, yeah, recognize that anytime you're subtracting or adding a negative number, that negative number is in binary going to be 2's complement. So say we're representing this range of numbers, we're going to need 4 bits because this is really the same range as 0 to 15. There's the same number of numbers. It's just instead of, so this is our number line, this is 0, it's 15 over here. Instead of taking this range, we're just shifting it this way and going from -8 to 7. Okay, so the range is still, this is going to be 4 bits. So that's, or n equals 4 bits. So the number of numbers we can represent is still 2 to the 4 minus 1. 2 to the 4 is 6, or sorry, we can represent 2 to the 4 numbers, and those range from 0 to 2 to the 4 minus 1, which is 16 numbers from 0 to 15. And this is unsigned. This is talking about what we've been talking about. When we move to 2's complement, this range from 0 to 15 is just getting shifted down to be from -8 to +7. That's still, if you count it up, that's still 16 numbers. This is unsigned. When we're talking about signed, we're now representing still 2 to the n numbers, but they range from -2 to the n minus 1 to 2 to the n minus 1 minus 1. And this is kind of like wordy, it's kind of complicated, but this is what you're representing. The same range, just shifted down so that about half of them are negative and half of them are not. Okay? So let's just do some examples for 2's complement, because I think a lot of this is a little like theory heavy, but when we get to examples, that helps a lot. So I think I have a good example, and we can just come up with more as we go. But so say we wanted to do 67 minus 15 in 2's complement. So the first step that I would recommend is figure out how many bits you need. So 67 is, what did we figure out that was? Yeah, it was 2 to the 6 was the biggest one, so we had 7 bits. Oh, maybe let's just do a smaller number to start with. Okay, let's do 9 minus 4. Okay, so 9 is usually 1, 0, 0, 1. But because we're working with 2's complement, we're going to need an extra bit. And the bit out front is going to be 0 for all positive numbers and 1 for all negative numbers. It is not to say that if this is 9, then 1, 1, 0, 0, 1. This is not -9. But you can, when you're working with 2's complement, the first bit, you can look at that and say, that's a negative number. And that's if you pad with zeros. That's if you write 9 like this, 0, 1, 0, 0, 1. So what I would recommend is figuring out how many bits you're working with, and then write all your positive numbers with leading zeros, and all your negative numbers, you're going to have a 1 out front. Then you don't get any messed up, because I know some people came to me with homework, and they'd written like negative, or they'd written +5 as like 1, 0, 1 in 2's complement. But in 2's complement, right, you would think that this is a negative number. So it's just a little bit safer to make sure that you're always writing the maximum number of bits, and you have a 0 if it's positive and a 1 if it's negative. Okay, so in this case, right, 9 is this. We're working with 5 bits. Okay, 4. This is 9. 4 in normal binary is 1, 0, 0. We're working with 5 bits, so I would recommend you do this. So this is a +4, the +9. We need this 4 to be a -4. So -4. That's where we switch all of the zeros to ones and ones to zeros. So 1, 1, 0, 1, 1, and we add 1. Okay, that's how we go from positive to negative. So 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. Is 1, 1, 1. So this is -4. Okay. And if you ever want to check yourself, you could add +4 back to -4, and you'd notice that everything would ripple and carry out, and you'd be left with all zeros. with an overflow. We'll talk about overflows in a second, but just this is an example. So now we have 9 plus -4 is 0, 1, 0, 0, 1 plus 1, 1, 1, 0, 0. So we add these 1 and 0 is 1, 0, 1. 1 plus 1 is 0, carry 1. 1 plus 1 is 0, carry 1. And so the reason I recommend that you figure out how many bits you're working with is so that you can recognize what the overflow bit is. So our answer is 1, 0, 0, 1, 0, 1. But that's 6 bits. We're working in 5-bit world. So the 6th bit is overflow. Yeah, so you ignore that bit because your answer is 5. This should be a positive 5. So whatever number we get should be, what is it? 0, 0, 1, 0, 1, because that's 5. And that's exactly what we got here, if we ignore this overflow bit. So that's, I would recommend figure out how many bits are good. 5 bits is what we're working with. So the 6th bit is the overflow bit. And whenever you get a 6th bit that's a 1, you discard it, yeah? So if
I know, like, but you can't because you can't only go over the first.
yeah, I guess if you have a negative number and you're going to a positive number, like if we were to change -4 back to a positive 4, so the answer is when you're changing from positive to a negative, every positive number is going to have a 0 out front. So that 0 should like absorb any overflows. Yeah. But I think if you're going from negative to positive, like if we wanted to change -4 is 1, 1, 1, 0, 0. Positive 4 would then be 0, 0, 0, 1, 1. See, that wouldn't even overflow actually, plus 1. So I don't think you're ever going to have a case like that. At the very least not. Because I think anytime you would overflow, it would just be like this leading 0 would absorb that overflow. So it would never be a 6th bit. But yeah, so this is how we do our arithmetic. So this overflow bit, and this is important. So we'll talk about overflow for a sec. When are you going to have overflow? So in this case, we had a positive number. We had a 9 minus a 4. And our result was positive number 5. So if this is positive, and this is positive, or I guess the way to think about it is we're always adding. If we're positive plus a negative, could this ever overflow? Yeah, so this will overflow, and that's fine, right? Overflow is okay because we've decided we're working in 2's complement, so we're going to handle all this stuff by just discarding the overflow bit. Otherwise, like if we didn't discard overflow, we'd be saying we're adding this binary number to this binary number. How on earth would we ever expect to get a smaller binary number? Right? That doesn't work. So the way we get around that is by discarding this overflow bit. By saying we're only concerned about this part, which is smaller. These 5 bits are smaller, right? But we can get an overflow when we're adding a positive and a negative number. If you were adding a, well, let me make sure I don't want to get this wrong now. I think there was a whole thing about it in the notes too. But overflow. Yeah, so the reason you would get, so I guess if we're talking about getting an overflow bit, that's like this case where anytime you're working with negative numbers. If we're talking about you add like 6 plus 8, or I guess 6 plus 10, and that gives us 16. But if we don't have the bits to work from that, so we're working with 5 bits. This is not a good example. Remember, 5 bits can represent anywhere from negative 2 to the n minus 1 to 2 to the n minus 1 minus 1. So when n equals 5, this is 2 to the 4, 2 to the 4 minus 1. 2 to the 4 is what? 16? Negative 16 to 15. So this is the number we're working with. If we're talking about when an overflow would harm our calculations, which is probably what you mean by asking, like, are you going to get an overflow? Because in this case, yeah, in this case, we got an overflow bit, but that's fine. We expected to. If we tried to, in 2's complement world, add 10 plus 10, we would not get 20 because we cannot represent 20 using these 5 bits in 2's complement. So this would be an overflow, right? And this is what Allison was saying. So if you have a positive number and a positive number, you may get overflow. Negative plus negative, also overflow. And you could think of that negative 10 plus negative 10 would not be negative 20 because we cannot represent negative 20. But anytime we have positive plus negative or negative plus positive, these are okay. Because you're not going to have an overflow that harms your calculations. You might get an overflow bit, but that's fine. We expect that. So like I could imagine there being a question about this exact thing. Like, when would there be an overflow? And it's possible, positive plus positive. It's possible, negative plus negative, but it's not possible for mixed signs. Yeah, within the range. Okay, so this is 2's complement. Do you want to do more examples of this? Okay. K-maps, K-maps, K-maps. So there might be some time at the end for questions if we don't get through any concepts, because after this is the 1202 review, and then we have some extra time. So if you're able to stick around between 6 and 7, I'll be here to answer questions. But otherwise, we can move on to K-maps. So K-maps, very useful for simplifying equations. Remember, you have to label the sides with gray code. Gray code is where from each term to the next, only one bit changes. And that's important. So I don't think you'll have to generate gray code because really all you need is for the 2 by 2 K-maps. But definitely understand that gray code is 0, 0, 0, 1, 1, 1, 1, 0. And even when it wraps around, only one bit is changing. Okay. So let's just start with an example. So here's a K-map. So you might be given an equation and asked to go to the K-map, or you might be given a K-map and asked to go to the equation, or a truth table, go to K-map, truth table, equation, K-map. You can do any of those things. So as long as you're comfortable going between them, that'll help you out a lot. So this is a K-map for a function that we're given, and we want to find the minimized function in SOP. So is SOP min terms or max terms? Min terms, right? So we're going to be looking for the ones in this equation, in this K-map. Okay, so we're going to be drawing our circles. So remember, step 1 is you want to draw the biggest circles possible. And then step 2 is you want to draw the fewest circles possible. So the biggest circles, you'll want to look for all the four size ones you can draw. You can draw one here, you can draw one here. And then what else can we do? We need to make sure everything is covered. We can do the pairs, right? So you can wrap around between the sides. And you can wrap around this way. If we had to, we could wrap around this way. And we can also do the 4 corners, makes a 4 piece. So we have our circles. Every one is covered, and we don't have any redundant circles. So next is writing out the equation. So F equals, and this will be the minimized equation if we have the minimum number of circles, which we do. So F is, let's start with this one first, this vertical 4 piece. So you want to look for what's staying the same and what's changing. In this one, what's staying the same is C and D, right? So this is just going to be C, D. The next one, this wider 4 piece, is going to be What's staying the same here? Well, A is 1 and D is 1. This is going to be A, D. And this last one, what's staying the same? So A and B are both 0 and D is 0 in both of these cases. So when A and B are 0, we're looking at A naught, B naught, and D naught. Because when we're working with min terms, if it's 0, that's A naught, right? These ones were all 1s, where like this one was where A is 1, so we had A without the inversion. Okay, so this is definitely something you'll have to do on the test. Next, this was SOP. Next, we could do the same thing in POS. This is the same function. When we're doing POS, this is going to be max terms, right? Max terms. So we're looking for zeros. And anytime we see that A is 0, that will be A. And where A is 1, it's going to be an A naught. And remember, things are going to be ORed together. This is product of sums. This is what we're going to be looking for. So let's draw our circles again, but this time we are drawing circles around the zeros. So we're going to be looking for any 4 pieces that we can draw. Does anyone see any? Exactly. So these are going to be wrapping around the side like this. We're circling the zeros. So for example, this one, how would we, so let's say this is f. This is still the same function f. It's not f naught. This is f, function f. So in this case, what's staying the same? B is 1 and D is 0. So B equals 1, D equals 0. So the max term for that, remember when B is 1, we're gonna write B naught. And we're ORing D. So this is B naught or D. That's this circle. Next, we can do the other OR circle like this. So in this one, A is 1. And what else is D is 0. So this one, we're ANDing these together. A is 1, so we're going to write A naught or D. And finally, the last one that we can draw is this 2 circle here. So A is 0. And then CD is 0, 1. So C equals 0, D equals 1. So this term would be A or C or D naught. Okay, so these would be our 3 terms. Just imagine if this one was written up there. Very likely that you'll be asked to do this on the exam. Get the max terms and get the min terms from a K-map. And this next question is to do exactly that. So this would be like in numerical form. So I'll just go back to the K-map slide for 1 second. So the way that you can kind of count through a K-map is you have to remember that you did it in gray code. So I like to count it like this. So the first square is 0, 1, and then you skip to the next one, 2, 3. Go to the next row, 4, 5, 6, 7. And then you go to the last row, 8, 9, 10, 11. Don't try to like figure out, calculate the binary each time. Just save yourself some time and remember what the order is. That'll help you out when you're trying to find the min terms. So because it's gray code, it doesn't go 0, 1, 2, 3. It goes 0, 1, 3, 2. And then finally 12, 13, 14, 15. So each one of these kind of skips over. And then you go, this is the first row, second row, third row, and fourth row, right? So you guys are familiar with this? So when we have a K-map, and we're asked to find the min terms, remember, are a sum of min terms. So we're going to be looking for the ones. So in this case, 0, this is M0. That's a 1, so we'll do 0, not 1. Oh, we can do the max terms at the same time. So remember, every function will have a set of min terms and a set of max terms, and those sets are disjoint. So whatever the min term number is, it's not going to be in the max terms, and whatever max term is not going to be in min terms. So that is to say, if we have the product of max terms, we can do this in a single pass. So this is the way that I would do it if you were asked to do both of these. So we got our minterms and our max terms. So M0, that's a minterm. We'll put it in the minterms. This is 1, that's a max term. Okay? And this is 2, that's a minterm. So we're going to put 2 there. And 3 is also a minterm. Next row, this is 4. This is M4. That is a max term. So we're going to go 4. 5 is also a max term. Does this make sense? Does everyone remember how to do this? Oh, so I don't know if your professor did that notation, but
I've seen the summation.
Yeah.
I just don't know.
I think you can do it like this. Like I've seen it like this before, like for the lowercase m for midterms. That should be sufficient. Yeah. Right. So 4, 5, 6 is also a max term, and 7 is a minterm. And then next we go to this row, right? It's gray code, so we skip this third row. Because we go 0, 0, 0, 1, 1, 0, 1, 1. We'll come back to it at the end. It's just like how we skip the third column. We go 1, 2, 3, 4.
So why is it in that?
That's a good question. The answer is because you're grouping up. So when I'm grouping up these 4 terms, what I'm saying is that, okay, when I group up just these 2 terms, when you write it like this, you know that the binary representation of this one and this one are only 1 bit off. And that's because we did it in gray code. So in this row, these are only 1 bit off in this direction, and they're in the same column. So the reason you're doing that is just you're grouping it together in groups of changing the minimum number of bits possible. And when a bit changes, then you could ignore that in the term, right? So when we're looking for what stays the same, like in this bubble, C and D are both 1. A and B are both changing in this entire bubble, so we ignore those. So that's the reason, because we gray code it like this way, when we're grouping them together, that lets us cast off the ones that are changing and keep the ones that are staying the same. So yeah, let's just finish up these minterms and max terms. So we were on 7. This is 0, 1, 2, 3, 4, 5, 6, 7. So this is 8. 8 is a max term. 9 is a minterm. This is 10. Remember, we go here, here, and skip to this one back. So 10 is a max term, and 11 is a minterm. And then finally, we do this third row, 0. That means it's a max term. So this is 12, 13, 14, and 15. Okay, so 12 is a max term. 13 is a minterm. 14 is a max term, and 15 is a minterm. So does it make sense? Does everyone understand that we're looking for wherever is a 1? Mm-hmm. Yeah, that's right. So yeah, we didn't get to BCD. We didn't get to rounding. Okay. Yeah, so rounding in binary is a little weird, right? So there's just the 3 rules, and you just have to practice it, right? So if you're rounding to this place value, you look at the next one. If the next one is a 0, round down. If it's a 1 and another 1 eventually, then you round up. So in this case, we're rounding to this one. That's a 0. The next bit is a 1, but that's followed by an infinite number of zeros. So in this case, this is the special case. If there was a 1 eventually, then we would round up because there's a 1 next and there's a 1 somewhere else. Okay, that's the easy case. This one you round down, this one you round up. The weird case is if you have a 1 followed by an infinite number of zeros. So like in this case, we would want to round so that this bit becomes a 0. So it's already a 0, so that means we round down. If this was a 1, then we would round up. So we would be saying that this would be like adding 1. So then this would carry, and we would get 1, 1, 0, 0, 0.
So thanks to the second one.
Yeah, so if we're looking at this place value. Okay. If we were looking at this place value, we would round down because there's a 0 next. Huh? Yeah. Did you talk about this in class?
Yeah.
Okay. That's what your professor said, right?
It was we just round. So you can have the odd or 0, which would be, so you want to round to which number is even.
Yeah.
0.
Right. 0 is even. Yeah. So it's the same thing, but you round to even is what the process is called, round to even. So you want to make sure that the number ends up being even. But yeah, this is the way, I think that this is the way that I learned it. Like you want to make that one be a 0 so that it because you're rounding to that place value, that's going to be the last place value. And for it to be even, you want that to be a 0. So a binary coded decimal addition is a little weird, but there's just rules. There's rules for it. You can look at those rules and you can practice it. If we have time at 6 p.m., we can do more examples of that. Also with converting between POS and SOP. Remember, if you have a K-map, if you're allowed to use a K-map, you can always get the minimized equation by drawing your circle. So like this is the same function. This was the minimized in SOP. This was minimized in POS. And you could go between those two without using any Boolean algebra properties or anything. So that's a lot more efficient. Sometimes you'll probably be asked to do these steps at least once, but you don't have to name the steps, I think. That was my experience, yeah. Like they could have taught you K-maps from day one, but they didn't. Right.
I would recommend for your test that anytime you have to do like anything with like equations like Boolean algebra or like going to POS or SOP, I would always draw a K-map. Like if it tells you that you have to do steps in order to simplify something, I would draw a K-map so you can check your work because that's honestly like a lot easier for you to check and make sure. And you can also see like, oh, which terms will group together and you can stack and simplify together. It'll like make it like a lot easier to draw a K-map like every time.
That's good advice.
More work. Yeah.
And
it'll like help you like make sure you don't make mistakes.
And if you understand how to get from the bubbles to the term name, so like if you understand how to get from this one is CD, then hopefully you understand how to go the other way. So you might be given a function and you have to fill out the K-map. So if you see the CD term, that means that it's a 1 anywhere where C and D is 1, and all the other ones are changing, okay? So think on that, practice that. We're kind of out of time for today, so we're going to move on to the 1202 section. But I'll be around for questions. How many people are taking both 2310 and 1202? Just about everyone. Okay. So this is convenience, I guess. Okay, you got to go. Do you have any more questions about 2310? Okay. Okay, sure.
I can't come back to station.
Sure. Okay. Well, reach out on the Discord. If you're on the Discord, you can ask any questions in the tutoring channel. I'm Isaac Brooks. And we're going to end this meeting and start a new meeting, right?